Good afternoon, everyone. Yeah, this talk was supposed to be given by Professor Vainarari, but is not here because of some official reason. So I'm his student, so I'll be giving the talk on behalf of him. So this is a multi-phase information diffusion in social networks. So first I'll start with introducing the field of the basics of information diffusion and influence maximization, followed by the problem of multi-phase diffusion and the solution approach that we have for it, followed by some of our results, both theoretical and practical, followed by some conclusion and future work. Okay, so you must be quite aware of these things, that social network is individuals and some connections among them. And the major effect of these connections is that individuals influence each other. And so one of the part of influencing each other is a passage of information from each other to each other. So this is used in something called as viral marketing. So it's like some seed nodes are selected by a company to whom free products are given. And then these people, if they like the product, they advertise to their friends, and they again buy the product, and they may again advertise to their friends, and this process goes on. So the company anticipates this and hopes that it's going to get a lot of product purchases based on viral marketing. But again, the company is not sure whether, in what direction this process is going to go. So how about the diffusion multiple phases? So it's like in literature, company are assumed to select the seed nodes in the beginning of the diffusion process. So we study what happens if we do this in multiple phases, the selection of the seed nodes. Okay, so coming to some current literature, like there is a vast literature on influence maximization networks for the past 1.5 decades or so. And but a lot of it is based only on a single phase diffusion. And basic idea of maximizing a particular objective function is used in a particular paper, which you can go through. We use this particular approach of multi-phase objective function maximization to the problem of influence maximization in social networks. Okay, so just to introduce the model of the independent cascade model. So I'm not sure whether it's been done in this series, but I'll anyway tell. So there is a weighted so there is some kind of a weighted directed graph which is given to us, and there is a probability PUV which is involved, which is associated with all the edges, and the diffusion starts at time step 0. So for example, if the company selects this particular node as the seed node, then this particular node has by default bought the product for free. Then he suggests this particular product to this person with probability 0.1. And again, so this person buys a product with probability 0.1. Suppose he buys it. So he becomes something called as a recently activated node. So in timestamp 0, he was activated. In timestamp 1, he gets activated. And suppose he again tells the other people to buy the product. So this is probability 0.2, 0.3. Then again, they buy the product with respective probabilities. So the important point in this model is that the recently activated nodes are the ones who pass on the information of buying the product to their friends. And the diffusion concludes when further nodes can be activated. Okay, so it's like this process proceeds in time steps, right? So at time step 0, the seed nodes are given the product. In time step 1, he buys the product. So what it means that if there was some other node here, okay, with probability 0.2, he's going to influence. So if in the first time step he was not able to influence him, so he cannot influence him further. So he was recently activated node only for time step 0, not in. Yeah, just the previous time step. Okay, so I'll just give a brief motivation. So again, it's intuitive why multi-phase diffusion should perform well. I will just motivate it with a stylized example. So suppose the company has a budget of 2, and this is the stylized social network given to you. So it's like, again, as I said, there are these directions of the influences, and there are probabilities associated with them. And this is like, if today gets influenced, then it's going to influence this set of nodes with probability 1. So that means. Okay, so again, there is something called as a live graph. So what it means is that it's like a graph that is achieved by coin tossing based on this particular probabilities. So it's like this particular edge will be present in the live graph with probability 0.5, this particular edge with probability 1, and so on. So this is like if node B gets activated, we cannot assure that node C is going to get activated, but it's going to get activated with probability 0.5. So this is what is captured in this particular live graph. So it's some kind of a reachability graph. Okay. So in practice, it's like what kind of a graph is going to occur? It's like this is the probabilistic graph which is given to us, but in practice, we are going to get one particular graph. So this is the instance of that graph, but we cannot see this in real life. It's what is underlying. So the main motivation for multiphase diffusion is to kind of uncover this live graph to some extent. Okay, so first we'll consider a single phase diffusion that is considered in literature, and the budget is 2. So suppose looking at this particular graph, some algorithm that wants to maximize the influence selects A and B as the seed nodes. Okay, so this is like green are like recently activated, and blue are going to be kind of not recently activated, which are activated in the past. So they cannot get involved in passing on the information. Okay, so in time step 0, these two are the recently activated nodes, and they influence this set of 100 nodes with probability 1. So this is the state of the network at time step 1. And then at time step 2, these are no more recently activated at the time steps, and the diffusion stops. Okay, so the diffusion stops at time step 1 with 202 influence nodes. So 202 these are 2 and these are 200. So can we do better? Again, it's like so here comes the multiphase diffusion. So suppose in the first phase only node A was getting activated. Node A is given a free product instead of both nodes A and B. So it's like we observe the diffusion, like how it is happening. So again, it's like it influences node B and this 100 nodes, and then B eventually influences this set of 100 nodes, and then we stop, and the diffusion stops because there are these are the recently activated nodes, but there is no outgoing edge from them. Okay, so in the second phase, we select the influence maximization algorithm may select the node C as the seed node, and then the diffusion will progress so that even this set of 100 nodes get influenced. And the diffusion stops at time step 4 with all the nodes getting influenced. Okay, so again, the motivation is the same, like using the same budget, we are influencing more nodes. So instead of selecting node C and B, suppose the influence maximizing algorithm would have selected node C, then as you can see that all the nodes are reachable from node C. So eventually as the diffusion progresses, all the nodes would have got influenced. So again, instead of using the total budget of 2, we are able to influence all the nodes with just a budget of 1. Okay, so our target can be achieved with. So the intuition is this. So the advantage is that seed set can be chosen based on the observed spread so far in the previous phase, and because of having more certainty about how the diffusion is progressing. But the disadvantage is that the diffusion may be slower because this is like a phase-wise selection of seed nodes. So there's a delay in selection of second phase seed nodes, and this may lead to compromise of time. And this may be quite undesirable in practical scenarios where there is some competitor, like he is also trying to diffuse some information, and if his information reaches some people first, then kind of your information is not so effective. Okay. So coming to the problem statement and the formulation. So this is the problem statement. So given the objective of influence maximization in a network using 2 phases, what should be the budget split? Like how should be the budget be split between the 2 phases, and what should be the delay between the 2 phases? And how do we select the seed nodes in the phases? Okay, so I'll just to introduce. So for single phase influence maximization, this is the objective function. Like if you select a seed set S as the seed set, then we have So this is like X is some kind of a live graph, and sigma X of S is the set of nodes which is reachable from the set S, and this live graph is going to happen with probability P of X, And so basically, there's some kind of an expected spread that we can achieve when the seed set selected is S. Okay. So on similar lines, we have S1 as the seed set for the first phase that we're going to select. We have AY as already influenced nodes, RY are recently influenced nodes. So again, AY is like influenced nodes which are no more recently, which are influenced nodes from past. Okay. Then S2 opt is the optimal set of the nodes which we are going to select for the second phase, based on the observation we see. So this observation is based on the live graph which is there underlying, the seed set that is selected for the first phase, the delay that is there between the two phases, and so again, K2 is like, it's not a part of observation, but our decision is going to be based on K2. Okay, so this is our objective function. If we select seed set S1 for the first phase, then I'll just take an expectation over all possible intermediate observations after the delay D. Okay, so this is that part for taking the expectation. And we are taking expectation of what? So it's like, we are going to get these are like already activated set. So what is the size of the already activated nodes after the time steps D? So that is when we are observing that's when we are making the observation Y. And this particular term is the term, based on the observation, we are going to select some optimal seed set, and what is going to be the spread of that particular seed set. So this is the term for that. I won't go into the details of this. So again, so basically just having some mathematical manipulation, we just reach this particular objective function. So this is like, we have over all possible live graphs, we have expectations over this of the S1, which is going to be selected as a seed set for the first phase, and the optimal set S2, which is going to be based on this particular observation. Okay, so we studied some properties of this objective function. So first is that it's non-negative, it's monotone increasing. So again, this is assuming that if I fix this particular budget split, like K1 and K2 are fixed, and the delay D also is fixed, so my objective is now only over this S1. Okay, for the moment, I'll extend it later to this D and budget split also. Okay, so keeping the budget split and delay fixed, what we have is that the objective function is non-negative, it's monotone increasing, and it's subadditive. So subadditivity just means that you have the function of the union is at most the addition of the two functions. But we observed that we showed that it's neither submodular nor supermodular. So submodular means that just consider two sets S and T, then the contribution that a node I is going to make to the set S is going to be at least as much as it's going to make to the set T. So it's like you have a group and a larger group. If you enter a smaller group, you are going to make more contribution. So that's what it intuitively means. So it's neither submodular nor supermodular. So this particular inequality is violated at least for one set of this one set of S and T's. Okay. But what we observed using simulations is that this diminishing returns property, that is this property of submodularity, is followed in most of the cases. Like for most S, T, I, this tuple, this diminishing returns property is satisfied. So there are some implications of this properties, like there are approximation algorithms for subadditive objective functions. There are approximate algorithms again for submodular functions and so on. So that's why we studied these properties to propose our algorithms. So we have, so one thing is, there is a problem with this particular objective function in the sense that it involves selecting an optimal set, which in itself is NP-hard, okay? So it's shown to be NP-hard in the literature, like in single phase influence maximization, selecting the seed set is NP-hard. So owing to this particular problem, we cannot actually compute this objective function for large networks. Okay, so what we have is we want to approximate the two-phase objective function. So, okay. So we propose some kind of algorithm for single-phase maximization itself first. Like instead of selecting the seed set optimally, we would like to select it in some other way. Like So consider this weight which we give to all the nodes. So this particular term is like the probability with which that node is not going to get influenced. So because of the diffusion which is already proceeding, it's possible that a node is going to get influenced because of the diffusion itself. In that case, there is no point of me selecting that node as a seed node. Okay. So this is the kind of probability that it's not going to get influenced by its neighbors. Okay. And this is the term which tells that if it gets influenced, then what is the expected spread that it's going to cause in one more time step. So this is like, so one is, okay. So this one is like, it's going to influence itself by default. And the summation, this is like the summation of this particular probabilities. Okay, so with this probability, it's going to get it's going to influence its neighbors. So based on this particular heuristic, we propose some alternative objective function for two-phase influence maximization. Okay, so this is first of all, just to remind, this is an alternative solution for an optimal seed selection. Okay, so based on these weights, we first choose the node with the highest weight, then we change the weights for all other nodes based on this particular formula, and we select the subsequent seed nodes. Okay, so this was our original objective function. As I said, it's impractical to compute this particular term. So we have, again, in literature, people have proposed greedy algorithm, which gives some kind of 63% guarantee on the optimal solution. So the problem is that even this algorithm is not practical. Like even this takes a lot of time to compute. And in our case, it's like this computation is only for this set. It's only for the computation of the objective function. It's not even for the optimization of the objective function. Okay, so this makes this also makes it difficult for the computation. So this is like we propose this whatever generalized degree discount algorithm. We use it for this single phase influence maximization for the second phase. So this is like 1,000 to 10,000 times better than greedy. It's like, it performs 1,000 to 10,000 times faster, and the results are almost same in terms of the expected influence spread. So what we showed theoretically is that this F and S, there is a theoretical guarantee. Again, the 63% still stays here. And empirically, we show that this particular objective function and this particular objective function, they are like empirically, they match. Like their values may not match exactly, but the seed sets that are getting selected because of using this and because of this, they are most likely going to be the same. So that's what we show using this empirical observation. Okay, so a general algorithm for two-phase influence maximization. It's again a very intuitive algorithm. So it's just that the main thing here is that if you use this approximate objective function using this, we call it farsighted objective function. While if we use the single phase objective function itself, we call it myopic. So it's like, okay, I'll just explain first. So suppose this is the graph given, and there are some probabilities which I have skipped putting here. So there are some probabilities on these edges. And based on that, some influence maximization algorithm select this set S1. So it could be done by maximizing either our farsighted objective function or the myopic objective function. So myopic objective function is like, we are given the budget split K1 and K1, K2, which adds up to K. So given K1, which seed node should be selected for the first phase? So I do not see farsighted, like I do not pre-see that there is going to be a second phase, there is going to be some delay or anything. I'll just assume that there is a budget K1, and based on that, I'll select a seed set. So that is this particular myopic objective function. So we study both this, like how they perform with respect to each other. If I use myopic versus if I use farsighted. So just run the diffusion until time step D. Okay. So again, these are like green are like recently activated, blue are like already activated. Okay. And suppose the time step delay has reached. Like these are like the seed nodes which are already activated now, and this is the recently activated node in the middle of the observation. So when we are going to have that intermediate observation. So time step D, we form this particular graph by removing this already activated nodes when we do the observation, because now they are not going to play any role in the diffusion anymore. And so we select the set of seed set S2, based on, so we know that this particular node, which was recently activated during the observation, is also going to act like a seed node for the second phase because it's a recently activated node, okay? So we have the sigma of S2 union Ry, that is the recently activated, on this particular new graph. And we continue the diffusion until no further nodes can be influenced. So the point here is that the seed set S1 is selected either based on farsighted or myopic. And for the second phase, it's selected myopic, assuming that the recently activated nodes for the recently activated nodes during the first phase are also going to act like seed nodes for the second phase. So coming to some results, okay, so one observation was that so we observed that myopic methods perform at par with farsighted, and they run again orders of magnitude faster. So the error involved was quite low, it can be like 1% or something. So that is the kind of error involved between myopic and farsighted, but it ran orders of magnitude faster. It depended on the size of the graph, but again for realistic graphs it was around 1,000 to 10,000 times. And so we have some theoretical results also for this. For you give me any value of K1 and K2, we can show that two phase will always perform better than single phase under optimal seed selection. And for any given values of K1 and K2, you can see it intuitively that the more observation we make, the more benefit is going to be. So that's what we show, that the two phase influence is maximized when the small d is equal to capital D, which the delay is equal to the longest path in the network. Okay, and this goes on monoton increasing as it's intuitively clear. The more observation you make, the more better you're going to have in the two phase influence. So these are some results based on our experiments on real world data sets. So what we see, the improvements are around 3 to 4%. So there are two models which are popular, weighted cascade and trivalency models, which are used for modeling the edge probabilities in a network. So I won't go into the details of these models, but yeah. So for weighted cascade models, for most data sets, it gave some kind of improvement of 3 to 5% on this weighted cascade model. And for trivalency model, it gave 5 to 6%. Okay? And this was assuming that the budget split is same. We have K1 equal to K2. Basically half split for both the phases. And we saw that the optimal percentage improvement was slightly higher than this K1 equal to K2 case. And the optimal K1, suppose the total budget was this much, then the optimal K1 was this much. So in all the cases, we saw that it was around 35%. So it's 1/3 of the budget should be given to the first phase and 2/3 to the second phase. Okay, so this is how the diffusion progresses. So a company would ideally like to see how the diffusion is going to progress with time. So as I said, because of two-phase diffusion, it's possible that the diffusion is going to slow down. Okay, so that's what we see, how much it slows down. So this is the gray plain line is the single-phase diffusion, and this dotted gray line is K1 you're giving for the first phase, and 200 minus 10 for the second phase, and the delay is 1. So I just wait for one time step between the two phases. So what we say is that even that has a marginal improvement over the single phase diffusion. And okay, just forget this number 14. This 14 is something this 14 you can consider infinity, you're going to wait for a long time between the two phases. In that case, if I split the budget equally, 100, 100, then this dotted black line is the result. And this is the optimal split, that is 70 for the first phase and 1/3 for the second phase. So in that case, this is the kind of graph that we get, and that is optimal. The final spread is optimal in that case. Okay, so yeah. So generally for studying this diffusion, right? So so you can use either real-world social network data sets. If otherwise, this is also an alternative that most people take in literature. Yeah, it's a collaboration data set, but yeah. So so structurally also it's kind of similar. Again, it's it's shown that in many papers it's shown that this particular, not only this, but many collaboration data sets have many social network properties. So our main problem was that because of the two-phase nature of this problem, and so in this single-phase diffusion case, people can study the diffusion on millions of nodes, or even more than that. But that is involving some kind of Monte Carlo simulations. For this to be calculated accurately, right? So they have some Monte Carlo iterations, okay? Because this cannot be exactly calculated. It's a sharply hard problem. So using Monte Carlo iterations to do it. But in our case, it's like, because it's a two-phase thing, we need Monte Carlo iterations for the first phase. Then, okay, just to give a picture. So a graph is given. So in single phase diffusion, we just have some possibilities and we just have some results, okay? Okay, so it's like in two phase, what we see is that we have this possibility, intermediate observation, and based on that, again, we have to make some observations. So it's like it kind of squares the number of Monte Carlo iterations. So because of that, we cannot study the diffusion on large data sets. So we only consider this is like a 15,000 node data set. Okay, so it's very difficult to go beyond this if you want to study the diffusion. So yeah, and most networks, social, yeah, okay, sure, yeah. So most networks, okay, so that is a thing. Yeah, but this is like structurally very similar to most network data sets. So this is a kind of graph that we have for budget split and delay. So, okay, I'll just explain this later. So the other side of the coin is that why not use two-phase diffusion all the time, and why not wait for the first phase to end so that we have the most observation possible. So the problem is, in actual life, the value of the diffusion decreases with time. As I said, the product value decreases with time, and we would like most of the nodes to buy the product in the initial stages. So we have this kind of a decay function delta, which is like after one time step, the product value decreases with delta, then delta square, and so on. So we have something called as cross entropy method, which is well known for optimizing an objective function, which doesn't necessarily have any particular properties. So we use this function. I urge you to actually go through this method because it can be used for many objective functions, irrespective of what else property they satisfy. So that method we use for optimizing over the budget split, the delay, and also the selection of the seed sets. So these are the plots for different values of delta. Like if you have delta equal to 0.85, where the product value decreases rapidly with time. So we have this particular graph where, I mean, it's really optimal to have give most of the budget to the first phase itself. Similarly, these are the values for other values of delta. And for delta equal to 1, that is, the budget is optimal to have delay as much as possible, and a budget split like, so this is the optimal point. So budget split is like 1/3 and 2/3, okay? So this is a 2D view of this plots, okay? So this is like for delta equal to 1, we have this for this one. And for delta equal to 0.95, just consider this optimal point wherever it happens, just cut the plot along that line, and this is what we have, and so on, okay? So what we have is that these plots are unimodal, like they just have one mode. So we can use some kind of method like golden section search, which are like efficient algorithms for optimizing unimodal functions. Okay. Okay. So I'll just conclude my talk. So we have the observation that under strict temporal constraints, it's good to use single phase diffusion itself. There is no point of going to multiple phases. So strict temporal constraint again means that the value of delta is very low. For moderate temporal constraints, use two-phase diffusion, but there should be a very short delay between the two phases, and you should allocate most of the budget to the first phase. In no temporal constraint case, that is the case which is studied in literature. You just study what is the expected influence without looking at how much value is going to decrease with time. In that case, use 1/3 budget for the first phase and 2/3 for the second phase. So again, the trade-off is between the size of the observed diffusion. So if you have more K1 and less K2, you will have good observation, but you won't have a lot of value remaining, a lot of budget remaining for the second phase. Okay. So coming to some quick future work, okay. So you can just look at them. So it's just, okay, one interesting direction is the study of a game theoretic setting. The game theoretic setting, which is studied in single phase diffusion. So what will happen if it's used in multi-phase diffusion? Okay, that's about it. Thank you.